Hello everyone, and welcome to the presentation of my thesis for Masters of Science in Artificial Intelligence and Machine Learning submitted to Liverpool John Moores University. And my topic is COVID-19 detection from chest X-ray images using transfer learning techniques. To begin with, let's understand the need of the study. As of now, COVID-19 detection and screening is done via the RT-PCR testing, which is considered as the gold standard for this. As of now, this technique needs special infrastructure because one person needs to take the sample from the patient and then further diagnosis will be done into the labs, which can be an expensive, and the accessibility of this RT-PCR test kits is also a subject to questions. So the motivation behind this study is to create an alternative system using the machine learning and deep learning technologies to create an alternative system for screening and diagnosis of COVID-19 detection using some existing infrastructure like making use of chest X-ray images or the CT scan images. And this machine learning and deep learning it has already been proven in the computer-aided diagnosis for the cancer and pneumonia detection in several areas. Let's see how we can make use of existing infrastructure for this diagnosis. As of now, we have multiple databases starting from patient and local and global databases available for all these other modalities. We can have some selection mechanism in which we can have multiple images of like MRI images, optical images, X-ray, CT and PETs. Based on these available images, we can build an AI-based image processing system which will do some training and help us classify whether this patient is COVID positive or not. We can evaluate these results based on the ground standards and then evaluate the performance of our testing mechanisms. For this study, we have chosen X-ray as our imaging technique because it is easily accessible and it is cost efficient, and we have a large number of data set available for the COVID classification for chest X-rays. As of now, there is an open accessible data set available which has around 30,000 plus images of chest X-rays from around 17,000 patients, which is also a labeled database. You can see that here we have a non-COVID X-ray and a COVID X-ray. Uh, the aims and objectives of the study is to enable a rapid classification of conventional chest X-rays in COVID and normal categories. Then we want to build a deep learning model using the existing pre-trained models using transfer learning techniques for assisting in early diagnosis of COVID-19 patients. And then finally, we'll analyze, compare, and report the performances of our different deep learning models and then identify the most accurate model for classifying the COVID correctly. Let's have a look at the related work that has been done in this field of COVID-19 detection using the chest X-rays. One of the initial study was done by Zhang and Zi, in which he has identified the viral pneumonia screening on chest X-rays using a mechanism called as confidence-aware anomaly detection, in which every X-ray has been assigned an anomaly score, and based on the score, you identify whether there is a normal X-ray or a pneumonia or a COVID-based X-ray. The training was done using the pre-trained model of EfficientNet, which was basically trained on ImageNet database. For this model, no COVID images were used for training, and hence the AUC and the sensitivity of this model is very low for the COVID X-rays. This was a very initial study that was done. After that, a significant study has been done by Hagnifer, in which he is using the existing chest XNet model, which was basically trained on the chest X-rays images and classify an X-ray into 14 different pathologies. The base model is used has been chest X-rays. As you can see in the architecture, this is the architecture of the chest X-ray, which is basically chest XNet, which is basically trained on a dense net architecture. After doing some pre-processing on the chest X-ray, this base model has been used in the transfer learning technique, and after that some custom layers, CNN layers has been added, and then final classification has been made. This was basically a binary and a trinary classification. The COVID images cap and the normal images was used for training, and the model was able to produce a 94% F1 score for the binary classification and 85 F1 score for the ternary classification. After that, some remarkable improvement has been done by Wang, Lin, and Wong in a study in which they have developed a custom CNN called as COVIDNet. This network was trained on COVID images, normal images, and the pneumonia images of the chest X-rays. They have used a different type of architectures into this model. The two important features of this is using the heavy using of the PEPX module, which is basically a projection expansion projection pattern, which enables enhanced representational capacity while keeping the computational complexity very low, which helps in fast training. And then the leveraging of long range connections. As you can see in the architecture, there's one cross one convolution layers has been used for the selective long range connectivity, which are basically connecting the long ranges of convolution from the earlier layers to the last layers, and these are the long connections. This study produced a three class accuracy of 93.3%, because the classification was done on three on the normal X-ray, chest X-ray, and then the normal images, COVID images, and then the pneumonia images. Much work after that has been done in the field of diagnosis of COVID using the 2D chest X-ray images. As you can see, the most of the machine learning techniques are using the transfer learning mechanism and using the dense net, VGGNet, darknet architecture for this. These work is done on a small data set. As you can see that there are very less number of COVID images that are being used for training. So the sensitivity and the accuracy can be in question for these particular models because it is not seen a large variety of data of the COVID data set. That brings us to our methodology. As we have already seen from the related work, that pre-trained model has been very effective in this type of classification problem. Hence, on the similar lines, we'll be using some state-of-the-art models and doing some experimentations around those to solve this problem. For that, we will have a X-ray dataset which has around 30,000 images across 17,000 patients. After that, we'll do some data pre-processing and augmentation. We'll do some sampling of the data to combat the problems that may arise due to the class imbalance problem, and we'll do some data augmentation like image sharing, horizontal flips, vertical flips, some translation, sharing, random zooms, and height, width, shift ranges, and then rotation. This will increase our model's capacity to generalize our model and for the new examples as well, making the model more robust for the new and unseen data. After that, we'll train our model using some existing pre-trained models, and finally we'll evaluate our model's performance and do some comparisons on the multiple experimentations done. The architecture of our study is like the data set will be feed to the some pre-processing. After that, it will be passed to the network which for training, which will make use of some pre-trained models, and then finally will produce the output, which is basically a binary classification. For pre-training models, we have chosen these 5 models, which has been proven and given very good result for these kind of classification problem, which includes VGNet, InceptionNet, ResNet, DenseNet, and ExceptionNet, which was basically trained on the ImageNet dataset for classification of images into 100 different classes. So we'll do some experimentation of these on these 5 models, and then we'll create a custom CNN models using these base models, and then we'll create the final output, and then we'll evaluate our model on these different architectures. After few experimentations, it turns out that DenseNet has produced the best results for our classification problem. Let's have a deeper look into this architecture. For our input data sets, images was passed to the model using the Keras input data generator with a batch size of 32 images to the network. Hyperparameters was tuned using the grid search CV method, in which the best set of hyperparameters was used for this training, in which we have used the binary cross entropy as a loss function, and for training and backpropagation, the optimizer has chosen as an Adam optimizer. This is the basic network architecture of our model, which was been trained using the DenseNet architecture. Firstly, our input is passed to the dense layer, which is our base model. The output of the dense layer is then passed to the global average pooling instead of a flattening, because it reduces the number of parameters, and basically a GAP does the average of all the values across the last axis. It takes the input tensor and computes the average of all the values across the width and the height matrix for all of the input channels. In this case, we have 3 input channels, as you can see from the input dimensions. After the GAP, we are passing the output to the dense layer. Dense layer basically performs a matrix vector multiplication, and the values of metric is nothing but the trainable parameters that we have, which will be updated and trained in the backpropagation step of the training. The output of this and the ReLU has been chosen as the activation function for this layer because it provides linearity, and it is basically reduced and it will really reduce the overall trainable parameters, and also speeds up the training process. After that, batch normalization has been used to make the model more stable during the training, because it normalizes the output of the previous layers and also helps the making each layer of the network learn more independently from each other. After that, the output has been passed to the dropout layer. We have chosen 20% as a dropout value. Dropout helps us in avoiding the overfitting during the training, as 20% of the neurons will be randomly shut off or ignored during the training process. That will make a new neural network in every pass, and it will help us reduce the overfitting, because a neural network has been seen to the different to data every time, which will decrease the overall compounding effect of the overfitting. Uh, After that, the model has been finally the output of it has been passed to the dense layer, which is basically using a sigmoid as an activation function at the last layer. We have chosen sigmoid because we are doing a binary classification. It ensures the probability between 0 to 1, and then keeping 0.5 as the threshold value. We'll have two classes, positive and negative. Uh, These are basic our model summary, in which we have a total of around 18 million total parameters, and the trainable parameter will be around 2 million, and non-trainable will be around 18 million. We just have 2 million trainable parameters because we have chose to freeze on the initial weights of the dense layer architecture. One of the reasons for doing that is because of the computational resources constraint that we have during the study. After that, the model was subjected to training. It was allowed to run for more than 30 epochs. It gives the best and optimal result in F15 epochs. So we are seeing the optimization in the 15 epochs. As you can see, for the training and validation loss per epoch, we can see that there's a very nominal training loss, but a significant number of validation loss has been done epoch by epoch. We can see that after 5 epochs, we have reached optimum point, but we can see that there's a drop after some of the epochs, and the most optimum value for the accuracy is already also seen on the 15th epoch. So we can see that the gradual decrease in the validation and the trailing loss, which has been optimal on the 15th epoch, and after that there was not much improvement on the losses and the accuracy, and hence we have chosen 15 we have allowed the model to run for the 15 epochs to avoid the overfitting for if we run it for further epochs. Coming about the performance evaluation of our models, as we have seen that DenseNet is our best model out of the 5 models. It gives us a accuracy of around 92%, precision of around 91%, and a recall value of 93%. This metric is our metric of choice, because this is a medical diagnosis problem, and in this kind of use cases, what we have to do is we want to have a high recall value, because we want to maximize our positives as classified as positive, because meaning that a positive COVID patient should be classified as positive, even if in that process we classify some of the negative patient as positive, because it has a less catastrophic value, and it will be less harmful if we do the otherwise. After that, we can see that AOC score is 97 and F1 score is 91. Here in the confusion matrix, we can see that out of total 400 samples of the test images, which was basically 200 positive and 200 negative images, we have correctly classified 187 as positives, and also 183 negatives. We have and 183 negatives as negatives. In this process, we were not able to classify 13 positive patients, which was incorrectly classified as negative patients, and 17 patients were classified as positive, while the truth was negative values. So in this process, 17 is the value that is of concern here, because 13 COVID positive patients were classified as negative in our process. So going forward, we want to reduce this number, and hence increase our overall recall value. doing the model comparisons of our different models. So we have chosen ResNet, InceptionNet, VGGNet, DenseNet, and ExceptionNet as our models. As we can see that the DenseNet is providing the best accuracy among all the other models, wherein the ResNet is providing a very good precision value, but very low recall value in this case. But we want to increase our recall value, and hence this model is not our choice, even if it has produced a good level of precision, because as per the use case we want to increase our recall value. After that, we can see that similarly VGGNet has already also produced a good a good precision, but a very low value of recall, and hence we have chosen our DenseNet as our model. And unsurprisingly, like this, DenseNet has been one of the deepest off-the-shelf network which has been used in this training, and due to this feature, it has been produced the best result so far. Comparing this studies model with some of the different models available in the related work area, is that one of the Chaudhary, which has produced a very good accuracy of 97% and also very high recall of 97%. Ichita also produced around 83% of the recall, and Lin and Lee has produced 92%, while this study is able to perform well and able to produce 93% of performance on a testing data set, while the other models were having using very low COVID samples images for training, and for also for validating the model, we have chosen a good number for training. We have chosen 30,000 images and around 400 images for testing of these models. Lastly, I want to conclude this presentation by giving some recommendations for future studies on this particular study. We have seen that this model was able to fulfill the aims and objectives, and was able to create a model with a good recall value. So this model can be used as a good alternative for the existing techniques, as existing testing techniques as RT-PCR that we have already discussed. But until then, we can use this model or this technique as a screening method to validate our model, and also as having an alternative technique in case we don't have any RT-PCR similar infrastructure available. For the enhancement of our model, we need to have multiple data sets and multiple data sources to generalize our model for multiple variants and multiple demographics. As of now, this data set has been specifically from one demographics. If you want to include multiple countries, multiple areas, multiple variants into the study, and the database can be expanded, the model will be able to perform well if it is be subjected to a training on a larger data sets. After that, more techniques and configurations can be explored to enhance the performance of our model. This was a basic study done on the comparative study for all the existing models, and using the transfer learning techniques. Also, lastly, we can also make use of some visualization techniques on the chest X-rays like GRUDCAM, which basically helps us identify like which area of the chest X-ray is basically responsible for the classification, so that it will be good in the explainability part of the our classification, because explainability is one of the major factor while using the deep learning techniques, because it is not very easy to explain and tell a normal person or a radiologist or a hospital or a doctor that how our model is being basically doing the training, and how it is able to produce a classification whether it's a COVID positive or negative. So we can make use of these kind of tech visualization techniques as well for better help us understanding the model better. Yeah, thank you.